Okay, so we are happy to have Michael McBreen giving his third microlocal talk.
Thank you, Roman. Sorry for the hiccup there. I, for some reason, couldn't join the Zoom room. All right, so let me put this in full screen. Today, I'm going to talk a little more about microdifferential modules, EX modules, and so forth. And then, well, in the sort of question session afterwards, I'll go back and discuss a few things from last time on microperverse sheaves. So I'm just going to sort of skip this section, which we did sort of at the end of last time, which you may have missed if you left on the hour, and start with the new material. So yeah, I'm going to talk about regular singularities, Cauchy-Lagrange filtrations, and the Riemann-Hilbert correspondence. So we start with some recollections. So if we have a D module, its solutions are Hom from your D module into the structure sheaf. If your D module is, presented as D of X modulo some differential operator P, then that corresponds to the usual notion of solutions, functions that are annihilated by P. And if your D module is holonomic, if its characteristic variety is Lagrangian, then the solutions functor lands in constructible sheaves. So in some sense, that's, you can think of that as one way of characterizing holonomic D modules. That's kind of the point. Now, it lands in perverse sheaves, but the functor is not injective somehow. There are different holonomic D modules with the same image. So the abelian category given by the image of this in constructible sheaves is the category of perverse sheaves. And you can holonomic D modules to get an equivalence. So first I'll recall what it means to be a regular holonomic for a D module, just very quickly. And then we'll sort of micro-localize that notion. So the rough definition is, say, you're regular along some subvariety if your solutions have polynomial growth near that subvariety. So example, if M is a D module on C, defining relation is Z dz plus 1/2 equals 0, then your solution near 0 over Z to the 1/2, so that is polynomial growth. But if you're Z squared d dz plus 1 equals 0, then your solution looks like e to the 1 over z. That is non-polynomial growth, exponential near 0. So the first one is regular, the second one is irregular. So a sort of more precise way, well, a precise way of defining regular singularities, which at least is the virtue of being very concise. So that you're regular at a point if after taking germs, germ of differential operators, germ of your D module, germ of functions. Formal solutions is the same thing as analytic solutions. So, or in other words, Han from your module into formal power series modulo convergent power series vanishes. And below there, I wrote down a sort of criterion in the one-dimensional case for being regular. Let me not go through it now, but it just generalizes these two previous examples. So our first goal is going to be to construct for regular holonomic D modules, the analog of nearby and vanishing. Sort of some of the basic tools in the microlocalization picture for constructible sheaves. And then we're going to use that to study some filtrations in regular holonomic D modules. And so the idea is sort of straightforward. You start with a function. You want to study, nearby vanishing cycles for that of a D module with respect to that function. You can assume that its zero fiber is smooth, and we just want to know sort of how to think of D modules near the zero, locally near the conormal bundles of that zero fiber. And the construction we're going to use is going to sort of make sense for a general smooth conic Lagrangian. So we're going to throw away this function and just sort of focus on lambda, smooth conic Lagrangian in what follows. We'll remember the function at the end. So, okay. So we start with a smooth conic Lagrangian. We let I be its ideal sheaf, functions that vanish on lambda. And we define a filtration of differential operators by saying, you're in the ith step if the kth power to the k minus ith power of lambda, of I lambda. So example, if lambda is the cotangent to the zero inside C, so its ideal is just functions divisible by Z. And here I wrote the zeroth step of the corresponding filtration. Okay, so you're basically filtering by, in some sense, the correct notion of order of vanishing at lambda. Not just order of vanishing of the coefficients, but yeah. So completing along this filtration, you should sort of think of as not near Y, so not near the submanifold, but near lambda itself, near the conormal. And so this is just sort of a mostly notational remark. So there's an analogous filtration on microdifferential operators that induces the one I described on differential operators. Just a tiny bit more annoying to define. And I'll occasionally go from EX to DX, DX to EX. So we're not going to worry too much about sort of the difference between the two for now. Okay, so we have this filtration on our operators, and we can also talk about compatible filtrations on modules. So if M is a coherent module, and again, lambda is a conic Lagrangian, then a filtration, a lambda filtration, I think these are now called V filtrations. This is some old-fashioned notation, but is basically a filtration induced by, which is compatible with the lambda filtration on differential operators, and which is sort of good in the same sense that our order filtrations on modules were good, meaning it's basically generated by some fixed lattice. Okay, so these are these are sort of well, clearly different from the filtrations we use to define characteristic varieties, compatible with a different filtration on differential operators. But this condition here is, formally the same. Okay, so 2 examples. If you start with M being well, differential operators on C modulo Z ddz minus alpha, which sort of informally you can think of as the D module generated by Z to the alpha. And you pick lambda to be, then, sorry, this D sub lambda notation, I forgot to explain that. It's just the 0th step of our F lambda filtration. But it's going to be differential operators generated by Z and Z dz. That just depends on lambda. And then our lambda filtration on our module is going to basically be by degree. You think of your module as Laurent polynomials times Z to the alpha. We're just filtering by the degree of the Laurent polynomial. And a higher dimensional example, but higher dimensional in a kind of a trivial way. So if you start with C to the N, and you impose so actually there's some relations missing there. So you impose the same relations, Zi d zi minus alpha I along some of the coordinates, and you just make it the constant D module along the other coordinates, just mod out by dzj, and you microlocalize to conormal of the singular locus. Then you're going to be filtering again by degree, but now it's multi-degree. All right. So in general, for a regular singular holonomic D module, you can construct a canonical lambda filtration for any smooth conic Lagrangian lambda. So I'll explain how to do that. And actually, parts of this construction work for holonomic modules more generally, but somehow the results are, I was not able to figure out how useful, the result is. So if anybody has any, opinions on this, on these lambda or V filtrations for holonomic D modules, I'm curious to know, because spent a lot of time trying to sort it out to no avail. Okay, so how are we going to construct this canonical lambda filtration? Well, in our examples, we started with a lambda, which was, again, the conormal of some submanifold y of x, given by, setting some variables to 0. And we just filtered basically by the degree in those variables. And implicitly, what we were using somehow is that we have this C star action on x, whose fixed locus is y, and such that the induced action on the conormal to y is just a scaling action, one that scales the fibers, conormal fibers, by the usual radial scaling. And then you of the C star action, if your module is equivariant, you can grade it, and that induces a filtration. So that's really what we were doing in those examples. Of course, you don't usually have this C star action, but you can cook up something that looks like it locally. So instead of a C star action, we're just going to define a local vector field on x along y. Doesn't need to be sort of consistent on overlaps. So we just pick such a vector field on an open cover of y. Or rather, on each set of an open cover, we pick such a vector field. And we'll grade m basically by the eigenvalues of this vector field. So same as we did by the degree with respect to the C star action. And the grading kind of depends on the choice of the vector field, but in fact, we'll see that this thing won't necessarily be strictly diagonalizable on our module anyways, but somehow the filtration by the size of the eigenvalues will still make sense and will be independent of the exact choice of vector field. And so that will give you this sort of global lambda filtration. So if y is cut out by zi equals 0, where zi is some subset of collection of local coordinates on x, then you can just pick theta as indicated. So it's the sort of sum of what's called an Euler vector field. So again, you see if you apply this to z to the lambda, where lambda is some multi-degree, it's theta applied to that guy is just the sort of, it's the part of the multi-degree associated to z1 through zk, the normal coordinates to y. So, okay, we have this vector field. Again, it involves some choices. We have to pick some local coordinates here, and definitely depends on those choices. But it is an element of the 0th step of our lambda filtration. So its image and the associated graded of the lambda filtration just depends on lambda. So it's a sign that we can use this to define some global object. So as a sort of, what we'd like to do is to grade things by eigenvalues of theta, more or less. And what allows us to do this is following theorem. So here again, we're assuming M is a regular holonomic. And theorem basically tells you that even though theta may not act diagonalizably on M, it the associated graded. So you can find a minimal polynomial. So given some section U of M, you can find some polynomial that B, such that B of theta takes U to a lower step of the filtration. And again, this minimal polynomial is independent of our choice of Euler vector field. And so it makes sense to define spectrum of U as the roots of this polynomial. So this is a substitute for the degree that we used in our basic examples. Somehow managed to make myself some very weak coffee. So any questions so far? This has been a sort of a slightly breezy let's say overview.
So B function for you, it's invariant of what? So what is exactly given and what? It's a section of the module, right? So we have start with a section of the module, and then we are looking for
yeah. But
so the variety close to smooth closed subvariety, or is it a divisor?
It's a subvariety.
Okay. Okay. Thanks.
And you can sort of extend this to the same definition works for, EX0 coherent submodules of your module. So you can define a B function for those guys too.
And again, in M, so we, for safety, assume it's regular.
We for safety assume it's regular, but somehow I think this particular theorem is also true in the holonomic case. Okay. So we have this notion of sort of the spectrum of a section of M, where sorry, this notation is a little bit telegraphic. When I say U is in M, what I really mean is U is a local section of M, some small open set, which can be an open set in the base or even an open set in the cotangent bundle. Take M to be an EX module. So so this Cauchy-Lagrange filtration, the V filtration, is defined using the spectrum. So the theorem basically says that if you take all the sections that have sufficiently small spectrum, so spectrum less than some integer L, you get a lattice. And then that lattice induces a lambda filtration.
So just to make sure, I think the spectrum was previously defined as like a subset of the complex numbers, and now you take its cardinality.
Yeah, so this just means the real part is less than this integer.
Real part of what?
Of the spectrum.
So it's like a subset of complex numbers, and you take real part of.
You take the somehow the real part of take just the projection onto R.
Okay. And you take the biggest thing?
Yeah. So it turns out that I guess there's this theorem of Kashiwara that I think in the regular holonomic case, the spectrum the regular holonomic case with spectrum is rational. So that's a non-trivial theorem. But in our case, of course, it could be complex.
Oh, wait, but if I just take the d module z to the lambda.
Yeah, with unipotent monodromy. So with
okay.
But yeah, so this notation again, yeah, it means when I say spec u is less than L, I'm thinking of spec u as some subset of the complex numbers, and I want it to lie to the left of the line given by real part of z equals L. To get this canonical filtration, it's actually super well behaved. So for instance, if you have a map of D modules, not only will it preserve the filtration, but it will strictly preserve the filtration. So you get some sort of like abelian category of filtered guys. Okay. But for us, the point of this filtration is it allows us to define an analog of vanishing cycles. So the idea is that if you take the associated graded with respect to our lambda filtration on differential operators, what you get is more or less differential operators on lambda itself. Not quite. You have to twist by the normal bundle to lambda, or rather by the square root of its determinant. Let me not dwell on why that is so, but somehow it's something you can sit down and think about in the case of a vector space. And so what this is telling you is that after taking graded with respect to this filtration of some dx module, what you get is you get more or less a module over differential operators on your conical Lagrangian. And this shouldn't be too surprising in the sense that we're localizing. The filtration's job is to localize near lambda, near the conormal to y, and we know in sort of our local picture, we know that we can take a Fourier transform to identify differential operators near lambda with differential operators along lambda. So this is just sort of confirming this expectation. So, okay, so fine. We started with a regular D module. We picked a conical Lagrangian lambda, and we cooked up a new D module, but now over differential operators on lambda itself. And so the theorem so again, I'm not really citing a lot of references here, but all of this material, to my knowledge, is due to some combination of Kashiwara and Malgrange and Bailenson and a few other people too. But the theorem says that basically this construction is a D-module version of vanishing cycles. So back to our original setting. So Y is a hypersurface, a smooth hypersurface. And lambda is its conormal bundle. And so, given such a thing, there's two things you could do. You could take the solutions of M, which is a constructible sheaf. That's the right-hand side of this equation. And you could take vanishing cycles of that constructible sheaf along Y. So that is a constructible sheaf on Y. Or you could instead do what we just did. So you could filter M with this lambda filtration, take the associated graded, so you get a D module on lambda, and then you could take solutions of that D module. And here, this gives you some constructible lambda, and you can restrict that to the to the section defined by the differential of F. That gives you a constructible sheaf on Y itself. And those two things are equal. So this is it's a slightly sort of cumbersome equality, but all it's really telling you is that you've successfully defined a D-module version of vanishing cycles. So this is the exact thing you'd want of vanishing cycles in a D-module case. It defines a D-module on lambda in a way which is compatible with Riemann-Hilbert correspondence with the vanishing cycle sphincter and constructible sheaves. Okay, and there's also, obviously a version of specialization in this context. It's something like nearby cycles. So let me quickly discuss a one-dimensional example of this setup. So we started with a regular holonomic D module, which is smooth along C star inside C. Maybe we can restrict a little disk around the origin. And we'll take lambda to be just a fiber over 0 in the cotangent bundle. And in this case, the previous theorem sort of simplifies. It's just telling you that vanishing cycles are given by the -1 graded piece of the lambda filtration. And here I added an extra bit that wasn't in the theorem. So the nearby cycles is given by the 0 graded piece of the lambda filtration. So this gives you a D-module theoretic definition of the nearby and vanishing cycles for the function Z. And so this is telling you that, okay, so these graded pieces, well, they're not all so the GR -1 is really telling you something about, your D module at 0, sort of the special singular behavior at 0, whereas the 0 graded piece telling you about the nearby fiber, pure D module. And so I've spelled this out some more, actually by by consulting notes from a previous seminar that Jordi ran in a different country in a different year. So I think I stole this from Brunebarbe. But anyways, so let me not go through this at length. I'll just sort of leave it in the notes for if you like. But basically the point is that if you look at the whole associated graded of the lambda filtration, well, you have operators x and ddx that increase or decrease the grading. And so you get a representation of this sort of double quiver. And because of the commutation relations between x and ddx, you know that actually the arrows in this quiver are all isomorphisms, except for the ones in the red box. So x, you know, just isomorphically maps the graded components into graded components for most values of the grading, and likewise. And so the only interesting stuff is happening between -1 and 0, exactly the two parts that intervene here. And in fact, so there's some equivalence of categories where you just map a regular D module to the -1 and the 0 graded part of this filtration, together with the maps induced by x and derivative. Again, this is exactly parallel to the classification of perverse sheaves on a disk, singular at the origin, by their nearby and vanishing cycles, together with the canonical and variation maps. Okay, so again, I left this stuff in the notes, but let me not go through all the details here. There's also a description of the sort of explicit correspondence between the vanishing cycles.
Can I ask, how is this example compatible with that general theorem you stated? Before you were, in that theorem, you were taking the whole associated graded, right?
Yeah, that's right. But I was sort of taking the whole associated graded, and then I was taking from, I was taking solutions of the associated graded as a D module. So, you know, the associated graded is a module over differential operators on lambda. And you want to take Ham from that into just the structure sheaf of lambda over the ring of differential operators.
Yeah, I mean, is it obvious why that's returning the -1 piece or whatever in the one?
Yeah. And
isn't it's the restriction to the graph, no? So
is that right? It's the restriction to the graph.
Like that big thing was, yeah.
This guy here? Or sorry,
yeah. Like that big thing on the left, that D module vanish, that curly underbrace thing is living on T star 0.
Yeah.
But then we actually want a vector space. And so we take a fiber of that thing on the graph.
Yes, yes, that's right. And somehow, of course, if you add 0 on the cotangent, then you sort of get the wrong answer. But if you take a generic fiber on the cotangent, then you're getting vanishing cycles. And so, yes, the point is that the graph is non-zero. Sorry, the D of F is non-zero along Y.
Yeah,
so yes, thank you.
Because also for this D modules on the line, well, the conical, you have Fourier transform and it interchanges the two vector spaces, psi and phi, and psi is actual nearby fiber, because if you just take this thing in quotient by, say, T-1, you get psi, and phi is nearby fiber of the Fourier dual. Right?
All right, thank you for the question and the answers. So, all right. So we have ourselves an example. Again, this is just sort of spelling out the explicit identification of the vanishing cycles of the solution sheaf and the sort of D-module vanishing cycles in our case. I don't worry too much about it for now. So in the second part of the talk, I want to discuss the sort of different filtration you can put on M. This one doesn't depend on the choice of lambda. So it's a filtration on your D module in the good old sense, compatible with the order filtration on differential operators, but which has the special property that the characteristic variety is reduced. And we can think of this as kind of a microlocal version of regularity. So just a quick recollection. So, the filtrations we consider to define the characteristic variety, everyone's compatible with the order filtration on differential operators. I use G rather than F here just to distinguish them from the lambda filtrations we were just looking at. Notion of a coherent filtration, which is one that's really sort of specified by a finite amount of data. And so what we're gunning for here is we want to show that if M is regular, it's a regular D module, then you can locally, or in fact globally, find a coherent filtration such that the associated gradient is reduced. Okay, in the sense that you take a function that vanishes on the single support, then it will annihilate the associated gradient. And not only will we find a local filtration, we'll actually construct a canonical global filtration that does exactly that. So just in some simple examples, this checks out. So if you look at our classic so their first D module, the C mod ZDZ, the associated gradient for the usual filtration is Z psi is equal to 0. So that's reduced, it's regular. And here actually there's a typo here that second example should be Z squared DDZ minus alpha. But anyways, the associated gradient is as described and it's non-reduced at 0.
But just to avoid misunderstanding, I think it's still possible to introduce a non-reduced filtration on a regular, I think, right? I mean, there is this natural one, but I can, being silly, I can spoil it, choose too many generators.
Yeah, that's
or maybe,
right.
Or maybe not in this case. There's a multiplicity maybe well defined, but in general, it's probably it should be possible, right?
Well, right. It does seem like if the characteristic cycle doesn't depend on the choice of coherent filtration.
I guess also if you can choose a random filtration, maybe that there will be torsion.
Yeah,
can be
That could
generically
be-
reduced, but not actually reduced, right?
Right.
Wait, why don't you just
right.
take a Hodge module? Then it's almost never reduced.
Right, right.
So, okay. So why do we want to reduce filtration? Well, I mean, we all have our reasons, but somehow one reason you might want it is because it's sort of yet another way of expressing the idea that microlocally, a D module should give you some sort of flat connection along its singular support. This is sort of, once you have this reduced filtration, this can be expressed in kind of an elementary way. So the idea is just that in that situation, the ideal modulo square, has a sort of Poisson action on the associated graded, which you can identify with an action of vector fields on lambda over its open part, over the smooth locus on the associated graded. And so this gives you sort of a structure of a vector bundle with a flat connection. So it is kind of nice because, well, constructing this reduced filtration is a pain, as we'll see. But if you just assume its existence, this is very elementary. Recipe. Okay, so to construct this canonical guy, let's just need some more sort of general microlocal notions. So basically, we're going to define the notion of microregularity for EX modules. So we first filter EX the same way we filter differential operators, by basically by order. So if you recall, EX was built in the analytic setting out of symbols to differential operators. So it sort of comes with a natural notion of order. And a lattice for us will just be a coherent EX0 module, submodule that generates the whole thing. So again, EX0 you should think of as something like, functions along the base plus negative order differential operators. Z plus the inverse of the derivative plus the derivative to the -3, so forth. And a coherent filtration on the EX module, just as in the DX module case, is just something generated, by a finite amount of data and compatible with this order filtration. Now, we're going to just generalize slightly what we already did in the case of a smooth conic Lagrangian. So here we allow lambda to be singular. For instance, it could be will be the characteristic variety of our EX module in our application. And we define the sort of quantized ideal of lambda. Sorry, that shouldn't be curly I of V, that should be curly I of lambda in part A of our definition. So So anyways, we define this quantized ideal to be just operators whose symbol vanishes on lambda. And then we define E sub lambda to be the subalgebra generated by these guys. So again, when lambda is smooth, we've already seen this. It's the zeroed step of our lambda filtration. And notice that E lambda contains order 0 microdifferential operators because their symbol vanishes by definition. So it's sort of order 0 differential operators plus those select, order 1 differential operators whose symbol vanishes along lambda, I think they generate. Just an example here, we take lambda to be the 0 fiber over the origin in C. And so our quantized ideal is order 1 guys, whose leading term is 0 at the origin. And then you just, E of lambda is everything generated by those guys. Okay, and so with this in hand, we can define microregular EX modules. So that's going to be, so an EX module has regular singularities if, remember, lattice is an E0 coherent submodule that generates the whole guy. For any lattice, its E lambda span is also E0 coherent. Okay, so a priori, if you act on your lattice by E lambda, you could get something much bigger. You might even get the whole thing. For instance, if you started with an irregular singularity, you might get the whole thing. But we say our EX module has regular singularities if what you get is still coherent with respect to the order 0 part, microdifferential operators. This is sort of a condition that looks hard to check, but is actually really not that bad. It's enough to check it at a single point in the generic locus of each irreducible component of the singular support. And the reason for that is that the sort of locus where this does not hold is involutive. So in particular, in the holonomic case, it's just going to be some subset of the irreducible components. Okay, I better hurry up because I'm basically out of time. So, okay, so as the point of this definition is just that it sort of micro-localized regular singularities of D modules. So under the maps between EX modules and DX modules, regular EX modules correspond to regular DX modules. Let me skip this slide. It's just explaining how you might prove such a thing. The point is that given a lambda filtration, you can try and cook up an order filtration in the following way. So if you remember, a lambda filtration was generated by its degree 0 part, L lambda. So L lambda is just the sort of zeroth step of your lambda filtration. And so you could try and just by using L lambda as your lattice. And this has the advantage that somehow it's reduced. But it may not be, a coherent order filtration in the sense that we like, depending on how you pick lambda. Okay, so this is, again, you've two different notions of filtration compatible with two different filtrations on differential operators. But starting from a lambda filtration, you can pick a step in the lambda filtration and then kind of like consider the order filtration generated by that step. That's what we're doing here. And so the theorem is you can do this in the case of a regular holonomic T module. So basically, what you do is you take lambda to be the support of your D module, the micro support. And you, on each smooth part of lambda, you have this Cauchoir-Malgrange filtration that we just discussed. And you take its zeroth step, and then you kind of glue those together along the sort of singular parts. And the theorem, the non-trivial theorem, is that having done this, you get something which is EX coherent, EX0 coherent. And so, which generates your whole D module. And so you can use that to define this global good filtration, coherent filtration on M. And by construction, it is going to be reduced. Okay, that's what we wanted. So I'm out of time. So let me sort of, I was going to say a few words about microlocal Riemann-Hilbert, but my words don't amount to much more than, you can prove such a thing. It was done by some combination of Andronikov, Washkis, and the statement is more or less what you'd expect. So I'm happy to answer questions about it, but I'm just going to skip the details. Well, that's it for this talk, and that's it for this series of talks. So thank you for listening. Here's a picture of Cauchoir, Teresa Montero Fernandez, and Shapira, which I found in an article of Shapira, I think, on the history of the subject. So it shows how glamorous we can aspire to be as mathematicians. Only we set our minds to it. So yeah, that's it for me. Thanks for listening.
Thanks. That's really, yeah. I'm out of words anyway. So any questions?
This is a very technical question, but who did you say is the person in the middle of the photo?
Teresa Montero Fernandez. She did some work on second microlocalization. That's how I came across her. I'm not sure. I haven't looked into it too carefully, basically. But she's also in the area.
it's not a very precise question, but can we compare again like this? So this Microlocal filtration, which led to definition of microlocal or characterization of microlocal regular singularity. And can we compare it to the just definition of lambda filtration? Is there some sort of, there was this theorem that you presented, they're related, but is there something that you can observe just by staring at the definitions? Like,
so right, so you want to go back to the sorry, where to is this the sort of slide you're thinking of?
Yes, so basically, yes, this is the slide I was thinking of, and I was trying to recall if there is a slide in the D module story before I got microlocal that this should be compared to.
So right, so you have E lambda here is the 0th step of the Kashiwara. So sorry, if lambda is smooth, if lambda is a smooth conic Lagrangian, then E lambda is just something we've encountered before. It's the 0th step of the Kashiwara-Malebranche filtration for lambda. For E of x. Or just the lambda filtration for E of x. And so what this definition is telling you is somehow, I guess, given any lattice, I can enlarge it slightly to make it compatible with. Sorry, I could try and like generate a lambda filtration, or by taking that lattice, sort of enlarging it by taking its image under E lambda. So that sort of forces it to be preserved by E lambda. And then I could then take the lambda filtration generated by that larger guy. And I suppose this definition is telling you that if you did that, the steps of this lambda filtration would be coherent.
So basically, I'm just trying, maybe you already explained it, but so if I start with the regular holonomic D module, then the theorem you quoted tells me that there is, if I microlocalize it, that this holds, right?
Yeah.
But, can I, but I probably can see it directly using the lambda filtration and microlocalizing it. Is that right?
See directly.
Just trying to see the, yeah, I mean, I think this microlocal part and the previous part of the talk, they have very similar flavor, but I'm trying to spell out the precise link, you know. Not at the level of statements of the theorem, but at the level of what we see at this stage.
I think that's right. So in the well, so maybe it helps to
Sorry, actually, maybe another question about this definition. So here, lambda is not necessarily smooth Lagrangian, right? But we only check the condition. But it's enough to check the condition at smooth points, right?
That's right. Yes.
Okay. Okay, and then yes, and then probably related to that lambda filtration. So
Yeah.
just a silly comment, but somehow, well, we kind of saw it on the one-dimensional example, but in the topological story, maybe in a sense more elementary, but just this microlocalization described topologically, microlocalization to a subvariety, kind of looked a little bit strange, so we had to specialize and then take Fourier transform and explain why this is relevant. And here it's, at least generically, it kind of pops out very naturally, right? You just you have to prove things, but if you have filtration and you take associated gradient, and like at least generically you get this action of the differential operator. You just basically pass from kind of, you have this Lagrangian and you can quantize your symplectic, you write your cotangent bundle near this Lagrangian in two ways, as thinking about it kind of.
Yeah.
You give out the base and thinking and localizing around the Lagrangian, and then just relation between these two things gives you this microlocalization. So.
But isn't this because we don't have a good microlocal perverse sheaves? We can't do it directly with them.
Okay, so that's so Kari, so your point is that EX is good, but like there is no, so EX module theory is good, but there is no equally good.
No, maybe some kind of play with some brains. Maybe somebody can. Right. I don't know how that.
Yeah, I mean, in sort of symplectic geometry, if you want to take the vanishing cycles, over some conormal bundle, you pick like a little Lagrangian disk that intersects this conormal bundle at a point, and then you take morphisms from that brane into this brane, and that somehow looks a little more. In a sense, it looks more simpler than choosing, some function whose differential intersects your conormal bundle at the point and so forth. Although, of course, I mean, in fact, it's no simpler because you have to set up this complicated machinery to talk about such branes.
One small comment. So why didn't you state you had this sort of comparison between the perverse sheaf side and the D module side? Why didn't you state that? You just stated that at the point. You didn't kind of state it in terms of specialization and Fourier transform. That's the statement. I wonder why you didn't say it that way.
No, I think
on one slide you just check that they agree on the points, and you chose a function to check that they're the same, but you didn't say that those local systems are simply the same.
I think, wasn't this last time?
No,
I mean, the notions that he had last time, on the previous slide, there was this statement of. On the previous slide, there was a statement where he exactly made that construction and get this lambda 1/2. Somewhere there was a statement.
Yeah. So you're looking at where is it? Here it is. Yeah.
Oh, right. Yeah. No.
This theorem.
I frankly thought it is already.
He didn't say that the right-hand side can be gotten by specialization of Fourier transform. So it's sort of a more.
Yeah. Sure. Yeah, I guess
then there's no function, and then there is no.
Right. Yeah.
Right. I suppose.
And it even explains the Maslov index because there's 1/2 over there.
Anyway. Okay, so that's a good point. So maybe this is somehow like not the. This is a little too specialized for its own good somehow.
Yes, it's too specialized for its own good. Yes.
but somehow, are you saying
so don't
okay, yeah.
restrict
No,
on the
I
left. On the left, and the psi f you replace with
the Fourier
with
transform
the
and the
Fourier
specialization.
transform, specialization of composed with Fourier transform, and then
Yeah.
it's correct.
Yeah. Right, and I guess maybe this is a good time to say, like in that situation, you don't need to restrict Y to be a hypersurface. Right, you could take Y to be some smaller codimensional submanifold. So then you no longer have vanishing cycles, but you can still do what Carrie is saying. So I guess this somehow the reason it is sometimes stated as I wrote it down here is just if you only know about vanishing cycles but don't know about specialization, then then this is a statement you can make.
But on the other hand, if Y is a divisor, that's pretty much the same.
Yeah. It comes to the same thing.
Right.
Yeah, and also it's maybe not a major point, but this twists by determined square root of a determinant. I guess there's an option of just consistently work with half differential operators twisted by half forms, and then they disappear, right?
So you, as in other words, instead of starting with a dx module, you start with a half twisted dx module, and then so so this is something which I
had raw shifts, I mean, for this
Yes.
program.
row sheaves. Indeed.
So
Of course, here you're taking principal divisor, so therefore this square root is maybe not so important because.
Yeah, there's somehow the normal
Anyway,
bundle has this canonical trivialization.
Right.
Maybe actually, I should also mention some corrections to previous talk, because so as Carrie pointed out last time, I had this sort of alternative definition of perverse sheaves, the sheafification of microperverse sheaves, sorry, as sheafification of perverse sheaves. And there were some objections to this because it's not clear that it recovers the official definition, microperverse sheaves. And I guess the basic point, I mean, so I don't know that we exactly found like an explicit, I don't know. So there's a map from the second definition to the first one. So the microperverse sheaf in the alternative sense defines a microperverse sheaf in the usual sense. And the worry is that not all microperverse sheaves are in the image of this map. So not all microperverse sheaves can be obtained by sort of starting with a, perverse sheaf and then quotienting by some stuff. We didn't quite write down an explicit counterexample, but roughly the idea is that in the first definition, you're defining perverse sheaves as a subsheaf of microsheaves, which in turn are really defined using real constructible sheaves on, subanalytic sets. And so you could have such a thing, which basically is, it's real constructible, but it happens to look perverse on some little open subset of the cotangent bundle. And it's not at all clear that such a thing would come from a globally perverse object on the whole space X. And Jordi also had some question about shifts, and why are there shifts in the definition of our microstocks? And I gave some answer of dubious, I don't know, wisdom. So I think one could actually just, Riemann pointed out, just get rid of these shifts. So you don't need to think about these shifts at all. So I think there's somehow like there's a question of normalization. So you have to identify your microstocks with objects of the derived category of vector spaces one way or another. But if you pick this consistently correct way, then the microstocks are just vector spaces, and your sheaf is perverse. So those are the two corrections to last time.
Thanks.
Can I just ask about what happened today? So it seemed like you were trying to define a notion of micro-regular or whatever. And then for D modules, regular is equivalent to some associated greater being reduced. Then you proceeded to define micro-regular in terms of lattices. It seemed like sort of completely different, although you...
Right. So there were basically, I guess, 3 different definitions of regularity that came up in the talk. The first was for usual D modules, the classic definition that formal solutions are the same as analytic solutions near every point. Then the second definition of regularity, which I introduced but didn't really say why it's equivalent to the first, is something is micro-regular if yes, every lattice, when you act on it by E lambda, gives you something which is still E0 coherent.
So here the lattice was already micro. He already
microlocal. Yeah, that's right. But somehow, so a D module is regular in the original sense if it's regular in everywhere in this microlocal sense. So I sort of didn't really explain why this is equivalent to the original classical definition of regularity, but roughly the idea is that as far as I understand, so this notion, this microlocal notion, is invariant under contact transformations. Sort of the advantage of all these microlocal notions is that they're invariant under contact transformations, and so you can sort of reduce to a situation by perturbing by contact transformation where your singular support is in generic position. So maybe let me go to the relevant slide. Yeah. So you perturb by a quantized contact transformation, and you reduce to a situation where lambda is in generic position over X, which means that it's the projection of lambda down to the base is C star to 1. And in this situation, you have sort of the same theorem as for microlocal sheaves in the constructible setting, namely your EX module actually comes from a DX module on the base, which also has regular singularities. And this is something you can kind of, why does this notion of regularity imply the usual notion in this situation? in this sort of generic position situation is something you can, to some extent, just check by hand, by calculation. So you can use this definition to reduce your EX module to standard form. Meaning, you can pick some clever generator such that this thing just looks like one of the examples I wrote down in the talk. And it's a polynomial in an Euler operator is your relation, and that's just sort of manifestly regular in the classical sense.
Wait, but so you say that you reduce to this generic position by contact transformation, but
Yeah.
do you mean to say that these contact transformations behave well with regularity? I mean, not micro-regularity, but regularity.
Well, right. What am I? So on the one hand, if you're trying to show that regularity implied micro-regularity, then
well, I mean, in some basic case, when I know for Fourier transform for conical D modules, I know it does preserve regularity. That's pretty much the only example of a contact transformation.
Right. Somehow, so I'm not going. I don't have a good answer. I don't have a great understanding of like the full proof of this equivalence. I will say, I guess you're not really supposed to be applying this contact transformation to the D module on the base. Somehow it's not quite clear what that would mean. So you need to find a way to avoid doing that.
Yeah.
So this reduction
maybe,
step.
Maybe you could, I don't remember exactly, but maybe you can say this microlocal thing by on D modules saying that there is an O-coherent lattice, which is somehow invariant under some things that some symbols that vanish on the Lagrangian. I think maybe that's a third definition of regularity, which you can give on the base. Because it certainly works in one variable. That's a standard old thing by Fuchs or somebody that they have to be some. In one variable,
right.
It certainly is correct.
Right.
So instead of saying EX0 coherent, you say O coherent, which is invariant under the same symbols that we discussed, but you just take them in D, but not in. Not in E.
Yeah.
I'm not sure. I forgot if that works, but it seems like a reasonable.
Yeah.
I mean, then it's the same definition as for E modules.
That sounds reasonable.
So I have a silly question. So on this slide, the last line, it's involutivity of what locus? Of irrational?
The irrational locus.
No,
so
irregular locus.
Irregular, sorry. So the bad locus. Yeah, which again it's just saying, so there's a locus on which the condition in the definition does not hold, and that locus is itself, involutive, meaning sort of coisotropic, more or less. And so if you're holonomic, that locus is just a union of irreducible components of your support. So.
So I guess this is, if I start with a D module, then any good filtration will produce something non-reduced on those components, right?
I think so, yes. Yeah.
Okay, any other questions? Okay, let's thank Michael again.
And thank you to Roman and Carrie for answering a lot of questions I had and correcting many mistakes. Yeah, and I'll try and post send out a like updated version of the notes.